have volcanoes erupting all over the world. In Colombia, Tanzania, Chile, Italy, the Canary Islands.
And here in Hawaii where we are, because that is the most active volcano on the planet.
So join us on an explosive journey as we take you right to the centre of the Earth. This is Volcano Live. It is 8 o'clock in the evening with you. It is 9 o'clock in the morning here. We are standing at 4,000 feet above sea level. It's a little blustery. It's a little, well, kind of cloudy and a little drizzly, but it is truly spectacular here. And over the next 4 nights, we are going to take you on an incredible journey and introduce you to the surprising and incredibly dynamic geological phenomenon that shapes and continues to shape our world, and that is, of course, volcanoes.
Because we're standing on one of the best. This is Mount Kilauea, one of the world's the active most volcano in the world. 500 years ago, a huge eruption blew out this huge crater. It's hard to see all the way around the cloud there. What you can see is across there the plume of steam coming out of that smaller crater. That's the wonderfully named Halemaumau crater. In there's a lava lake. And the thing is, a few years ago, 5 years ago, that plume of cloud wasn't there because in 2008 this happened.
This incredible explosion that rocked the crater created that lava lake, and
these big plumes coming out of kind of red stuff, just creating that.
It must have been the most amazing thing to witness. And a little bit later in the programme, we will be talking to a scientist who did indeed witness the birth of that lava lake. But the great thing is that we have been working over the weeks leading up to this series with the scientists who are based here at the Hawaii Volcano Observatory. This is one of the best studied volcanoes in the world. They've been here for 100 years. They have provided us with all sorts of expertise and experience, but also some fantastic footage. And they sent us this footage of the lava lake just to give you a sense of what's going on under that plume.
Look at that. I mean, these things are really rare. It's one of only 4 current lava lakes in the world. Look at the turmoil going on there.
It's a sort of witch's claw, isn't it?
Down, I want to dive in there.
You do. Don't do that yet. We can't get any closer to it because sadly the gases coming off that lake are highly poisonous. But we do have technology on our side, and there is a webcam right down there. It's updated roughly every 15 to 20 minutes. So let's have a look at the latest image from that webcam, which gives you a sense. I mean, it is just black and white, but the white cracks, presumably, I mean, that is molten rock at hundreds, if not thousands of degrees.
Yeah, nearly 1,000 degrees. You get rafts, it forms across, but it's constantly moving. You don't really get a sense of it in that black and white one.
So what we need is a thermal camera. Do we have one? Of course we do. Look at that.
Now that's it in action, isn't it? So what you got is you can see the lava breaking up and moving across. Every now and then you get these what's called gas piston explosions. Look at it bursting out. And then what's great is the lava goes in the opposite direction. So it's hugely turbulent, a lot of turmoil going on right there.
And that is strange, really, because you think of a lake as being a rather sort of still and placid place. So why is that lava moving so much?
Well, what's happening is the magma that's deep underneath our feet, as we'll learn much more, is just constantly coming up and keeping that thing going. But the thing is, we're not just looking at Hawaii, because our planet is far more dynamic, far more volcanically active than you might have guessed. So here's a little look at what we've got in store.
Over the next 4 nights, we'll take you to some of the world's most spectacular volcanic landscapes. From dazzling lava flows above the ground
chambers hundreds of feet below it.
It's just a riot of every colour you can think of.
And we'll discover what it is that makes our planet so dynamic and exciting.
Tonight I report from Iceland to find out how a volcanic eruption there caused chaos in the UK.
Armed with fizzy pop and chewy mints, Ed Byrne recreates a volcanic eruption in a garden in Bristol.
That's a reasonable height of spark they got there.
And kicking off a series of global expeditions, our cameras head to the Democratic Republic of Congo and the breathtaking lava lake of Mount Nyiragongo. So there is plenty to look forward to over the next 4 nights. But before we go any further, let's have a little look at where we are, because we are about as far from the UK as is possible to be. You can see that we are in the middle of the Pacific Ocean. There is the Hawaiian archipelago. It's a chain of islands. We're on the big one there at the bottom, known locally as Big Island. And those islands only exist because of volcanic activity.
Yeah, I mean, it's hard to believe it. We are standing above a huge plume of hot rock that's coming out. And so what we've got is that produces Kilauea, which is behind us here, which isn't your classic volcano. It's not your classic cone shape, but as we'll discover over the next few days, volcanoes come in all shapes and sizes. Further along that way, we've got lava coming out of fissures in a lava field that's active at the moment, spewing out. There's wonderful images of that.
We've got some images of that. Let's have a look at this. So this is about 10 miles from us. This is happening as we speak. This area has been erupting since 1983, and it's that makes Kilauea the world's most active volcano. Absolutely. I mean, it's mesmerising stuff to watch, isn't it?
That red stuff. There's something about the red stuff, isn't it? But it's not just up. Just over here is Mauna Loa, just beside us there. Now that looks like a nice gentle hill, but it's actually the biggest volcano on Earth. The second biggest, nearly second biggest on the entire solar system, which is just unbelievable.
It is unbelievable because it looks so innocuous. It looks like a rather gentle Welsh hill just outside Abergavenny.
But that one, in many respects, is a really tricky one. It's got an eruptive cycle that goes every 8 years on average over centuries, but it hasn't gone since 1984, which is about just over 25 years ago. That's one we'll definitely be keeping an eye on.
And scientists here are definitely keeping an eye on it too. Now, the more we discover about volcanoes, the more questions seem to arise, not just from the scientific community, but from all of us who've been working on the series. Every day we wake up with a head full of, how does this work? Well, you, I hope, might feel the same, and if you would like to get questions into us while the show is going on, we'll try and answer them throughout the programme. To do that, you need to go to bbc.co.uk/Volcano Live. You can also tweet questions at #Volcano Live. At the moment, we have a live web chat going on via our website with Dr. Clive Oppenheimer from Cambridge University. He's a volcanologist, and if we fail to answer your questions, he certainly should be able to.
So given that volcanoes are erupting all over the world, why is it that we came to Hawaii?
Holiday shows, Hawaii Five-0. Yeah, we all know that Hawaii is a tropical paradise of blue skies, crashing surf and bronzed bodies. But scratch below the layer of sun cream and you discover that Hawaii is alive. Big Island is made up of 5 volcanoes that fuse it together. Over the last 700,000 years, their eruptions and outpourings have pushed new land above the waves of the Pacific. For volcanologists, it's about the most exciting place to be on the planet. Exactly 100 years ago, the Hawaiian Volcano Observatory, or HBO, was founded to try and understand how these volcanoes work, a task it still performs to this day.
Our first order mission is to issue timely and accurate warnings of volcanic activity, earthquake activity in the state of Hawaii. In order to do that, of course, we have to establish and maintain 24/7 monitoring of the physical parameters around volcanoes and earthquakes. Although it seems simple to be issuing the warnings, there's a lot of background work that has to be done, a lot of history that has to be acquired, and interpreted and reinterpreted. Every time we learn something new, we have to go back to the old records and see, well, did we see that back in 1950?
The HVO is contained within the Hawaii Volcanoes National Park, a vast area that is geologically vibrant and whose landscape is ever-changing.
This is the edge of Kilauea Caldera.
This park has the most active volcanoes in the entire world. Here we can see the eruption of Kilauea at its summit. And so here people can come, very accessible, from all over the world, and they can actually see in our lifetimes rocks being formed. And typically we think about rocks being formed in millions and millions of years. And here it's in a human time scale. In minutes and seconds, hours, days, months, you can actually see rocks form. So this is an incredible laboratory where you can feel and see the awesome power of this planet.
The volcanoes haven't just shaped the land, they've helped form one of the world's most vibrant ecosystems, home to unique plants, birds and animals. And they've had a profound effect on the people who live here, giving birth to a rich culture.
In Hawaii and in our culture, our ancestors came here to the edge of the crater, to Kilauea, and they came to honor and respect Pele, the goddess of the volcano. And still today we show that kind of respect by coming here and giving a ho'okupu, the leo, the voice, that chant.
Oh, that just makes the hair stand up on the back of my neck every single time I hear it. Now we've come down from the crater rim, which is just up there. This is our little technical hub.
This is home.
Very small and neat. That is a horse box, but at the moment it includes our producer and our executive producer and directors and all sorts of screens and things. Satellite beaming us live to you in the UK. Now this is one of the most important members, if not the most important member of the Volcano Live. We like to call her Mini Winnie. Now she may look like a camper van to you, but oh my goodness, she's got a secret inside here. Mini Winnie is the only mobile volcanic hub that we know of throughout the entire world. And here we are plugged into not just what's happening in Hawaii, but all over the world. This will give you a little sense of the geography of where we are. So we are about here at the Ma'uma'u crater. Here is the enormous Mauna Loa, so it gives you a sense of scale of just how big this volcano is. The lava flows that you saw happening down here.
Yep.
So we are in, we hope, the right place.
So this is the volcano control room, and what we're going to have, we can get maps and things like that, and access what the latest volcanic activity is. So this is a map of all of the known volcanoes on the planet. All these are, it's about 1,400 that we know have erupted in the last million years or so. But not all of these are active on a daily basis, and there's about 60 active a year. This is what's active right now. There's about 25, typically between 20 and 30, 25 volcanoes today active in this. The most active places around the Pacific. This is the Pacific Ring of Fire, so volcanoes all the way around here, and right in the middle, right there in Hawaii, that's where we are.
Now, the great thing about modern science, modern volcanology, if you like, is that webcams give all of us a great view of what is going on. We saw the webcam earlier in the bottom of the crater here. Many of these volcanoes have webcams on. We know that there is a volcano in Guatemala that is active at the moment. So that's that one here. And let's go up to the webcam there. Oh, actually not terribly active by the looks of things.
You can see it's today.
Yeah.
And it's a beautiful volcano, lovely shape, and you can just see a little bit of activity. We get these daily reports from the Smithsonian, which is the place that summarises all the activity. So we'll keep an eye on this. But the other one is the wonderful Popocatépetl.
I'm glad you said that.
In Mexico.
In Mexico, so just here. Let's go to the webcam of that. Oh, that's great
today's
picture.
one. Well, yesterday, I don't know if we can see it. Here we go. Now, this is about 2 weeks ago, this started kicking off, and it was producing ash plumes. And the worry is, Mexico City is just down there, huge conurbation, so definitely keeping our eye on that one.
And you too can keep your eye on all the webcams attached to these volcanoes by going to our website, bbc.co.uk/volcano live. But what is it about these volcanoes that makes them happen?
Well, one of the things is, what all volcanoes have in common is they give off heat. But one of the big questions is, where does that heat come from?
Heat is everywhere in Hawaii. If it's not beaming down from above, it's boiling up from below. But if you really want to get a sense of the searing heat produced by Hawaii's volcanoes, you have to take to the air. This whole landscape is a hardened crust of lava that's spewed out of the Pu'u'o crater just 15 miles from Kilauea summit. It looks grey because the surface has begun to cool and solidify. With the naked eye, you just get the odd glimpse of the tremendous heat that lies beneath.
Except if I look at one of these, which is a terrible camera, that whole landscape just transforms.
Those red areas are around 500 Celsius. The white parts are even hotter. They're over 1,000. The tremendous heat that's inside the Earth is what's melted the rock that fuels all the world's volcanoes.
Well, the question is, why is the inside of the Earth so hot in the first place? Where did all this heat come from?
To answer that question, you have to travel back 4.5 billion years to the formation of the planet itself. Our world began life as little more than a jumble of rocks, colliding with each other as they circled the sun. These impacts were so violent they generated a huge amount of heat, some of which remains trapped inside the planet to this day. But the violent collisions are only half the story, because the rocks themselves contain radioactive material, and that material also became trapped inside the Earth.
It's hard to believe, but we live on a radioactive planet. I mean, you get a sense of that from this. This is a Geiger counter, which measures natural radioactive decay in the rocks around me. Decay from radioactive elements like thorium, uranium, potassium that have been trapped inside the rocks since the planet was formed. And the point is, the decay of those radioactive elements generates heat. So if I take a rock like this is uraninite and it's rich in uranium, and I put that to the Geiger counter, look at that. It's off the scale. And although that's rich in radioactive elements, it doesn't cause us any harm, it doesn't really generate much heat. And in these rocks, these basalts, well, they've got even less radioactive elements in them. You just get the odd click. Because we've really got so much rock, all those tiny amounts add up. So that if you take the planet as a whole, there's just such a huge amount of rock that it produces a huge amount of heat. In fact, half the heat that's trapped inside the Earth comes from radioactive elements.
When combined with heat from other sources, like the violent collisions that formed our world, there's enough to heat the core of our planet to 5,500 Celsius. That's as hot as the surface of the sun. Yet incredibly, most of us live our whole lives without even noticing the inferno beneath our feet.
That's because our thick rocky crust, the solid ground that we live on, acts like a blanket keeping the heat inside. But it can't contain it forever, because although it's blistering hot down there, up there in space it's freezing. Planet Earth is this hot rock hurtling through the frozen depths of space, and like any hot object that's surrounded by cold space, our world is cooling, which means the heat that's trapped down there wants to get out.
And that's what causes all the volcanic activity on the planet. Heat is transported as molten rock, magma. It seeps up through fractures in the ocean floor. It burns up through weak spots in the ground, and it forces its way through cracks in rock, erupting onto the surface in spectacular explosions. From humble vents of steam to dramatic fiery mountains, volcanic activity is all caused by the same process. Heat from that inferno beneath our feet escaping to the surface. But it's wrong to think of volcanoes as just great vents in the earth. They are white hot windows into the inner workings of our planet.
You can see that the clouds are partying, Halley Mau Mau craters now in all its glory. Absolutely fantastic. Now, one of the kind of misconceptions that drives us geologists absolutely mad is the idea that beneath the solid ground that we're on, there's this molten ocean of magma. It's just not the case. If you slice through the planet, then what you'd reveal in its layers is something like a pineapple, because what we've got here is the pineapple's got a hard core, really, and that is the metal dense core of the planet. And then round that, the fleshy part is what is the Earth's mantle, and then we've got this tough outer skin, and that's the crust. And the point is that both the mantle and the crust are solid rock. But while the crust is kind of cool and rigid and brittle, this rock in here is hot, plasticky, and it flows kind of like plasticine. But the thing is, where does all that molten stuff come from? Because down here the temperatures are easily enough to melt rocks. It should be molten. What stops it from being molten is the pressure. The sheer wear of all that rock above squeezes it solid. And now, the thing is that volcanoes exist in those places where those mantle rocks are able to melt. And in Kilauea, what that means is that deep beneath us we've got a plume of hot rock that rises up from the core and rises up and like a blowtorch kind of melts its way through the ocean crust. And because it rises up close to the surface, there's less pressure holding it in, so it's able to turn from solid to liquid and then rise up, making its way through the crust and pulling in big magma chambers. So underneath our feet is just a huge magma chamber, maybe just 1 mile down, and it's several hundred feet across. Eventually the pressure in that magma chamber builds up and it bursts out as volcanoes. I mean, it's complicated stuff. Does that make sense, Kate?
Made perfect sense. It's amazing what a geologist can do with a bit of tropical fruit. Well, as we said, that magma chamber creates volcanoes. This was created in 2008, and one of the people who was lucky enough to witness the birth of that lava lake was Jeff Sutton. Jeff works here at the Hawaiian Volcanoes Observatory. You have possibly the best office in the world, don't you?
It's really, really nice, yeah, especially on a morning like this.
It is, it is. So can you just talk us through the birth of this lava lake and what happened, what you saw?
Well, it took about 5 months or so for it to become apparent that something was really going to be happening. In late 2007, we started, in November, we started seeing levels of seismicity increase, and then in December, gas emissions started going up really high, and by mid-January, the gas emissions were very, very high.
So that's something that you specialise in, yes, isn't it? And so those gas emissions going through the roof, if you like, told you something's going to happen.
That's right. By kind of mid-January of 2008, the gases being emitted by fumaroles around the rim of Halemaumau were already at what we, for Kilauea, is an eruptive gas composition.
Right.
And so we knew something was up at that point.
And then what happened?
Well, and then the next month, the SO2, the sulfur dioxide emissions were high enough that park visitors were having to kind of be drug out by emergency vehicles because just because the ambient sulfur dioxide concentrations were so high. And so the park wisely decided, I think, to close down that half of the caldera. And about a month later was when this new vent opened up on March 12th, and it was an area of fuming. And a few days after that, those at nighttime, that fuming area began to glow red. It looked a little bit like, from the observatory, it looked a little bit like a kind of a campfire of glowing embers.
And how long did it take before you realized that what was going on was the formation of a lava lake?
Oh, that came actually a little bit later. I mean, we knew something was going on, but it wasn't until about a week or so later after that there were two of us in the observatory at about 3 o'clock in the morning. One of us was just getting to work and to begin the day of work, and the other of us hadn't gone home yet. And over the course of a couple of minutes, the glowing ember, the campfire thing, kind of collapsed. It got dark, and then the next thing we knew, the overlook visitor fence was made of wood, had caught on fire, and everything else was dark. And then we noticed a little bit further across the crater, a big sulfurous area, or an area of sulfur deposit, had actually caught on fire. And sulfur burns with this kind of eerie blue glow, and it must
have been an unforgettable moment.
So far, yes.
Jeff, thank you very much indeed. Well, the role of scientists like Jeff at the HVO is to constantly monitor this volcano. As Jeff has indicated, there is always things going on here. One of the things that gives scientists a clue as to what might happen next and when is the lava in that lake, as geologist Matt Patrick explains.
I'm Matthew Patrick. I'm a geologist at the Hawaiian Volcano Observatory, and my job is to observe and understand the volcano. Our mission here is to gain a better understanding of how the volcano works so that we have a better sense of what the hazards might be. Just taking a simple photo or making an observation with a point and shoot can actually be a pretty powerful tool, but we go a step beyond that, and we deploy a number of cameras, both visual cameras and thermal cameras, and we put them out in the field so that they run continuously and make 24/7 observation. It also gives you views into areas that are just much too dangerous to access with people. The plume in back of me that you see is very thick, and it obscures the view in the vent to the naked eye. The thermal camera, though, is very useful in that it can see right through that fume, and it actually gives you an image and a picture of that lava lake activity. It's revealed a number of things that we just wouldn't have been able to see with the naked eye. A year ago, what we had was a very spectacular eruption down on the East Rift Zone. Effects of that eruption were actually felt at the summit. The result was that the summit lava lake drained catastrophically, and we were able to capture that with a thermal camera. Another important part of my job is monitoring the flows in the East Rift Zone, finding out where those flows are and where they're going to move. With the helicopter, we can get these broad views of the activity on the lava flow field. Tracking these lava flow fields is very important because there are communities actually that are on the edge of the flow field. So it's a very important part of our job to get a very precise location on where those flows are. So during my time here, we've used the camera systems to capture some really spectacular processes. Things like crater collapses, lava lake draining events, delta collapses, a whole host of activities. So what's really remarkable about working here is that these absolutely spectacular processes are happening on a daily basis, and we get to see them just as part of our daily routine.
So what's clear from Jeff and Matt is that we're on a living, breathing volcano, and one that occasionally has its tantrums. The other thing, though, is that this is also a part where thousands of people visit every day. And so the responsibility of keeping them safe is with park rangers like Jim Gill. Jim, that is a hell of a responsibility, is it not?
Yes, absolutely. But we really try to let people get as close as possible with our trails, our roads, our viewpoints, so it's an approachable, a place where people can have a first-hand experience of the volcano.
Because I was kind of surprised. You can come right up to the edge without fence. I mean, here, I don't know if you can see this. Everyone's getting nervous here, but there's a huge crack here running along right behind it. Now, at some point, I'll follow. Isn't it a worry that people can just come up to these really sharp edges and fall off?
Well, we have a whole campaign in about how to view lava safely, so people can learn before they come up the hill.
Yeah.
When they come to the park, they know to bring a flashlight, to wear boots,
So what is the relationship that visitors would have with this wonderful volcano?
Well, the relationship is that they're right here when it's erupting. And so they can see it and, well, have a really safe experience. They have an incredible safety record with millions of visitors, and everyone leaves and has a fantastic memory of the park.
Well, Kate, I'm sure you'll agree, it is the most fantastic place to see a volcano. Thanks, Jim.
Yeah.
Kate.
Thank you very much indeed, Ian. I'm sorry if you are experiencing a few little sound problems from our end. We are, as you know, in the middle of the Pacific Ocean. Now, we may not have any active volcanoes in Britain, but we certainly have a lot of active volcanologists, and we've taken terrible advantage of them. We've given cameras to some of them that are going to the remotest parts of the world on their ongoing quest to try and understand how volcanoes work. And one of them has taken a camera to possibly one of the most volatile places on Earth, a very, very long way from where she lives.
Before becoming a volcanologist, I used to work in mobile telecoms, and I decided that I'd really like to do something more interesting. So when I got made redundant, I decided this was an opportunity and made the decision to go back to university to study geology. I went and did a PhD at Bristol, so I've spent the last 4 years having an amazing time studying volcanic rocks and working out how a volcano works. I was just coming to the end of my PhD and I really wanted a holiday to celebrate the end of studying. I'd always wanted to see a lava lake, and the largest one is in the Democratic Republic of Congo. Unfortunately, this isn't the safest place in the world. For the past 20 years, there's been nearly constant fighting. And one of the largest United Nations forces in the world is there to try to maintain peace. I travelled with a company who have visited that area of the Congo very regularly over the last 2 or 4 years. So I was happy that provided I took various precautions, that it would be perfectly safe to go. I left for Congo's Volcano Mountains, a chain of 8 volcanoes. They stretch for around 50 miles across part of the African Rift Valley. We're just about to set off for Goma and the Virunga National Park, where we're hoping to see 2 volcanoes, Nyamulunga, which has a really large lava lake, and Nyamuragira. We had no idea what we were going to see when we got there, because nobody had visited the volcanoes since the beginning of December. We were driving along in the car, and we looked out of the window, and there were these very strange clouds. And I looked at it and I thought, I'm sure that's a volcanic plume. The clouds were just a different shape and a slightly different colour to the background clouds. And we could hear faint noises in the distance like thunder. So we just couldn't wait to get to the site. We had an 8-kilometre hike through the rainforest before we'd find out whether or not it was erupting. We came out of the rainforest, and there in front of us was this 100-metre high scoria cone with this amazing fire fountain. And it was just an incredible sight, and the noise was unbelievable. Although they ended up over 500 metres away from the actual eruption, you could still feel the heat from the volcano. Normally, when you see geology, it's happened over hundreds, thousands, millions of years. But this was geology in action, this was live, this was rocks being born right in front of us. It was an amazing day, and as it got dark, the show was even more spectacular. as night falls, you get the incandescence from the lava, which you don't see during the day. So it really brings the fire fountaining and the whole volcano to life.
Just a little bit jealous. I mean, that is an incredible thing to witness. And we have another part of Lorraine's extraordinary journey to the Congo a little bit later on in the programme.
I think what's nice is it just shows that volcanoes work in kind of different ways. That's a very spectacular eruption. But actually, one of the things about Hawaii that's interesting is it tends to have quite mild, gentle, what's called effusive eruptions. And basically what we get is fissures open up, and we get some pictures here. You get runny lava, the very, very fluid that flows. I mean, this is going quite fast. Here's a bit slower. It goes a bit walking pace, but it's just beautiful.
So these are the lava fields just basically over the mountain from us here, aren't they?
Absolutely. Isn't that gorgeous?
It's so basically what we're seeing is more a kind of seeping rather than a kind of spurting.
Exactly. But Hawaiian volcanoes are also capable of throwing the toys out the pram. They can start eruptions with what's called fire fountains, which is where you get fissures or vents that throw jets. This happened in 1959 at Little Kilauea Iki, just down the road. And what that is doing is it went up nearly 2,000 feet.
What?
Nearly 2,000 feet. Huge fire fountains. And what Lorraine was seeing was smaller versions of those. So the irony is that that's actually what's still called effusive, because it's just chucking out magma. Some volcanoes can basically get so explosive, they rip apart the volcano and throw ash, thousands of feet up into the atmosphere, and we'll see those later.
So that would be what you would call an explosive eruption, as opposed to an effusive eruption. And is that when you get your more kind of classic cone shape of volcanoes?
Yes, absolutely. So in Hawaii, you can see how low it is. It just seeps out, produces these very low volcanoes, but other ones are your classic steep ones.
Well, we set Ed Byrne a little challenge. We said we would like you to be able to demonstrate to us the difference between effusive and explosive eruptions. So he did it, but he started in the supermarket.
I'm in Bristol, a city which contains a surprisingly high concentration of some of the world's leading volcanologists. Shortly I'm going to be meeting one such volcanologist, but before I do, he's giving me a shopping list of things to pick up. Golden syrup, how much is lots? It'd be a shame to show up with 6 bottles of golden syrup and have him go, I said lots! Thick sugar, there's no such thing as thick sugar. 5 bags, 6 bags, just to be on the safe side. There we go. Diet Coke. It does seem strange to buy this much sugar and then have him insist to buy a diet drink, but...
And finally, loads of Mentos. Presumably these volcanologists don't like bad breath.
There ain't no party like a volcanologist's party.
Up at the University of Bristol, I'm meeting with a man who sent me out shopping, Dr. Jeremy Phillips. Apparently, he can use my ingredients to help me understand precisely how and why volcanoes erupt.
I'm good. Very nice to meet you.
And you, sir, and you.
Excellent. You got our shopping?
I have. I hope I got the quantities right. I got lots of everything.
That looks great.
We're heading to the courtyard for an experiment with my Diet Coke and Mentos. Now, just in case you think I'm being paid to mention Diet Coke and Mentos, I'm not. Believe it or not, academics have proved that they really are the best combination for simulating a volcanic eruption.
Well, volcanoes erupt magma, which also contains dissolved gases, just like the Coke does.
Right.
And it's the bubbles that result from those dissolved gases that are really the main driving force behind volcanic eruptions.
Right.
In this experiment, the bottle represents the volcano, the Diet Coke represents the magma, which is a liquid which contains dissolved gases, just as Diet Coke does.
And the Mentos represents any catalyst that makes bubbles form.
I'll just screw up the top.
5, 4, 3, 2, 1. That's a reasonable height of spark we got there.
Yes.
Magma is filled with dissolved gases, but just like our Diet Coke, it needs a surface to allow it to erupt. As magma rises towards the surface, the pressure drops, causing crystals to form on which bubbles can grow, exactly like with the Mentos when they enter the Diet Coke. This is known as nucleation. And as the growth of these bubbles forces the magma upwards, it causes an eruption. Okay, but here's the thing, not all eruptions are the same. Some fire out lava fountains and lava flows, like in Hawaii, while others explode out ash and pumice. So what makes the two types different? Apparently, it's all down to how easily the gas bubbles can travel through the magma, which is where the golden syrup comes in. So we know how bubbles create eruptions. We've seen that already with the Mentos and the Coke. So this is how bubbles in different levels of viscosity of magma create different kinds of eruptions.
In this experiment we have two tubes that contain golden syrup. Golden syrup is a sticky liquid, a viscous liquid, and it represents magma in these experiments. Okay, so I'll start the experiment. I just turn on the gas. This just contains the golden syrup, and what we can see, because the bubbles can pass easily through the magma, there's no opportunity for any real pressure to build up inside this system.
And so we're just having a quite happy, bubbling volcano like the guys are sitting watching in Hawaii right now.
Exactly right.
But not all magmas are the same. Some are stickier than others, which is why we've added sugar to the second tube.
I'm going to turn the gas on in this tube, and what we can see is the surface rises up to a much greater height. That's showing that there's more pressure in this tube as a result of the fact that the gas finds it much more difficult to pass through this more viscous magma.
Some volcanoes have lava which isn't particularly viscous, so bubbles can escape relatively easily, and their eruptions tend to be less violent. They're known as effusive eruptions. However, with the stickier, more viscous magma, bubbles can't escape. Pressure builds, and you get explosive eruptions. But the thing is, when you have an explosive eruption, it's not molten lava thrown into the air, but billowing ash clouds. So where's all this stuff coming from? The answer lies with the massive drop in pressure which viscous magmas experience as they erupt to the surface. In this tube, we have our very viscous, gas-rich magma, represented here by a mixture of acetone and pine resin. We're creating pressure in the tube roughly equivalent to what magma is under inside the volcano. By releasing this pressure, we should see what happens to magma when the volcano erupts and it's suddenly exposed to the much lower pressure of the atmosphere.
So I'll open the valve. Here we go.
There she blows. Cool.
Well, so what is this now then? So this is then
what you can
solidified resin now is coating the whole of the
what
inside.
you can see what's on the inside of the tube is that pine resin with its acetone removed, preserving the textures of the bubbles that were there as it accelerated and flowed up the tube. In explosive eruptions, the pressure drops rapidly. That means that the volatile gases inside the magma can expand and accelerate the mixture up through the volcano, as we saw in the experiment, and then what we're left with is a material called a pumice. Pumices get generated during large explosive eruptions, and then they get ground up to form the ash. So as they flow up through the volcano, they collide with each other and they collide with the sides of the pipe that they flow through, and they get ground up, and that ground up pumice becomes the ash that gets exploded out to the top.
So there you have it. Some volcanoes just bubble away, some pour molten lava out all over the place, and some explode, shooting rock and gas and ash into the atmosphere. And it's all to do with composition of magma, crystals, viscosity, pressure changes, and Mentos. What were the Mentos again?
Yeah, I have to say I'm still a little confused about the chewy mint What do they represent in real life?
So the two you mentioned, the coke, are places where the gas that's dissolved in the coke can attach itself and grow.
Yeah.
Down in the magma, it's crystals that do that. The gas attach themselves to crystals, the pressure builds up, and it explodes to the surface. That's what it's trying to get at.
And what fun!
Yeah. So,
I mean, who knew you could have so much fun with fizzy pop and some mints? Now, we have had lots of your questions coming in. This is one of my favourites, and it comes in from Joseph Jones, who's 8 years old, from Rugby, and he wants to know the difference between lava and magma, because he needs to explain it to his teacher.
Oh dear, okay, so basically magma is the liquid rock that rises up, and lava is what's produced when it comes out at the surface.
Oh, perfect, so it's only lava when it comes out on the surface. There you are, Joseph. Hope that will explain that to your teacher. Lee Hankinson contacted us via Twitter, and he wants to know, thanks Lee, what would happen if all 5 of the Hawaiian volcanoes went off at the same time? I mean, is that technically possible?
It's very unlikely. The ones in the north are more or less inactive now. The ones that are active, Mauna Loa, this is Mauna Loa here, that is a tricky one. It's got big lava flows, and they can come down here and take out, Hilo here, which is the main town. So that is a big worry. And of course, Kilauea here, now that's the one right on our doorstep. If that goes, I guess we go off air. That's what happens.
So we do. Well, keep your questions coming in. As I say, we'll try and answer some more as the programme goes on and throughout the series. But for those of us in Britain, we tend to think of volcanoes as being something rather exotic, quite exciting, but they happen elsewhere. So when a volcano erupted 1,000 miles away in Iceland in 2010, obviously most of us thought that it would have no impact on our lives whatsoever. How wrong we were. In April 2010, we experienced the biggest disruption to air travel since the Second World War.
Travel chaos after more than half all flights in Europe were grounded today.
Hundreds of thousands of passengers were left stranded.
One of the world's busiest hubs has been brought to a complete standstill.
The source of the problems was the Icelandic volcano Eyjafjallajökull, and it continued to blast huge volumes of ash into the atmosphere for over a month. Today, the scene here couldn't be more different. Well, this is it. This is the culprit, Eyjafjallajökull. This is the volcano that caused all that chaos back in Europe 2 years ago. And it looks so benign and so beautiful now. A great, shining, pure, white glacier. And it's strange, I thought that there would be somehow more evidence that the landscape would still be blackened. I mean, there was tons and tons, untold amounts of ash that poured out of this crater. And yet now there's so little sign of it up here. Most of the ash has now been buried under 2 years' worth of fresh snow, returning much of the summit of the volcano to a pristine whiteness. We're flying directly around the crater now, where you can smell the sulphur in the air. And it's a quite extraordinary contrast between the thick glacial ice and the exposed, steaming rock that's the very heart of this volcano. It's just an incredible sight. Immediately after the eruption, the glacier was turned black. A huge volume of ash had caused disruption for much longer than expected, and it all came from what is a relatively small volcano. So where did all that ash come from? To find out, I head for the summit of the volcano itself. We climb 1,500 meters over glacial ice, finally arriving at the crater's edge.
volcanologist Bjorn Oddsson is part of the team that has discovered why this volcano produced such a large and long-lasting eruption. We've come as close to the edge of Eyjafjallajökull's main crater as we dare. Beyond here, the icy walls of this new gash in the ice are extremely unstable, tumbling down to the steaming vent below.
Why ash? Why did this volcano generate so much ash?
That's due to the volcanic happening under ice. So it produces a lot of meltwater, and the interaction between the lava and ice breaks up all the lava and forms ash, which is transported into ash plumes and dispersed in the atmosphere.
So instead of what I think of, I suppose, as a classic volcanic eruption with huge amounts of lava spurting out of the top of the volcano and pouring down the sides, because it happened under ice, you had this reaction that you described, and it turned not into solid lava, but into this powdery ash.
Yes. If it would happen on a dry land, then we would see lava flowing around, and it would mostly be effusive, as we call it.
Right.
But when we mix water and magma, it turns explosive, and all the product is ash, but not lava.
During the eruption, 250 million cubic meters of ash were blasted high into the atmosphere. Long-lasting high pressure over the Atlantic created strong northerly winds, which carried the ash towards continental Europe and forced the cancellation of thousands of flights. To explain why, Bjorn has brought some ash from the 2010 eruption along with him.
Wow. So this is the very ash that came out of this volcano in 2010.
Yes. It was these fine-grained ash. It's a little bit muddy.
Yeah.
This is the fine-grain that gets the highest in the atmosphere and is carried most way from the volcano.
So this would have been the stuff that caused all the disruption in Europe?
Yes.
Right.
It might look harmless, but this strange muddy substance has the potential to inflict real damage on aeroplane engines.
It's mostly glass. It's volcanic glass.
Right.
So when it gets into the jet, it melts, and when it cools, it covers the jet engine inside and produces a breakdown in the jets. So it's this fine-grained glass.
Fine-grained ash like this is often produced at ice-covered craters, but most eruptions only produce ash for a few days. So why did Eyjafjallajökull continue to pump out ash for well over a month? As Bjorn's team have discovered, the reason relates to something that had been lurking inside the volcano since well before 2010.
It seems like the magma from last eruption has been resting under the volcano since 1821.
New evidence shows that an old pocket of magma got stuck within the volcano nearly 200 years ago, and it's been lying in wait ever since. When Eyjafjallajökull came to life once more in 2010, the old magma was stirred up, and it too emerged from the crater, adding to the volume of ash and extending the eruption for much longer than expected. So the legacy of a 19th century eruption was enough to bring modern-day Europe to its knees.
We may not have seen the last of Eyjafjallajökull. History tells us that we could be entering a period where Iceland's volcanoes play an ever-increasing role in our lives.
The eruption of Eyjafjallajökull has proved once again that we can't take any volcano for granted, even a small one, in a country 1,000 miles away. Events here have shown that all volcanoes have the ability to teach us something new, valuable lessons
which could help us to better understand the next big eruption.
It was amazing that a volcano that had lain apparently dormant for 200 years caused so much chaos, which brings us to another question from one of our lovely viewers. Hello, Hilary Keats. She wants to know why can a volcano like Eyjafjallajökull lie apparently dormant for so long and then suddenly spring back to life?
It's a really important question. I mean, the key thing is that it takes a time for those magma chambers to fill up with magma to get the pressure to blow. Yeah. But you can get times when the magma just is cut off completely and it's permanently extinct. The really difficult thing for volcano scientists is knowing when a volcano is dormant or one's extinct. And in fact, most of the big volcanic disasters happen from volcanoes that we think have just completely finished.
So it's really that question of waiting for the magma chamber to refill up, and that's when it will blow.
Yeah, absolutely.
Okay, well, thank you very much. Thank you, Hilary. Keep your questions coming in. As you have seen, there is still a lot that volcano scientists don't know about these amazing geological phenomenons. Lorraine Field is one of those scientists who is trying to uncover a little bit more information about them. And now let's go back to her report from the Congo and another of its extraordinary volcanic wonders.
It's fantastic.
It really is.
I love it.
After a few hours sleep, we were up early for another look at the eruption site before we packed up for the long hike out of the park. So next we headed to Nurindonga. At 2 miles high, it's one of the most famous volcanoes in Africa, and it's been my ambition to see it for the past 4 years. The trek up Mount Nurindonga is actually exceedingly tough. Those are the huts on the summit that we're aiming for. When we finally reach the summit, you're really elated because you've reached the top, and you rush inside the crater and you look down and all you can see is fog. The lava lake should actually be down there somewhere. You kind of have this vision in your head, you've seen the pictures, so you get there and you think, yes! And then you look over the edge and it's white. And you think, oh no. As time went on, you got these tiny little glimpses of sort of pink incandescence below the fog, where it was just beginning to clear, and you think, yes. And then eventually the whole thing clears and you just have this amazing view. You'll have this incredible feeling of being on the edge of the earth, and you look over and you have this deep pit and there's a lava lake at the bottom, which you know is connected down into the magma in the earth. So you're almost looking into the centre of the earth. It's quite magical. I just knew that as night fell, it would look even more spectacular. The whole crater is filled with pink. It's quite an unreal colour. If you're standing below the crater rim, the whole sky lights up with this pink coloration. It was way more than I expected. It lived up beyond expectations. It was really interesting because it brings everything that you study to life. You realise that there are so many interacting forces. It's given me a lot of insights into how eruption happens, which I can apply to work going forward. Studying volcanoes has completely changed my life. I've got a better understanding of the earth that we live on, for a start, but also it's completely changed the job that I do. I can't wait to get up in the morning and come in to work now, whereas 10 years ago, Monday morning, had that Monday morning feeling, didn't want to go into work. And now this is such a large part of my life, and I get excited about everything that I do now.
That footage is absolutely exquisite. It's geopoetry, that's what it is. Absolutely gorgeous. But what's interesting, what you've got to remember really, is that this lava lake that we've got behind us here is down in there. It's 160 feet across. That's an Olympic-sized swimming pool. Lorraine's one, 5 times bigger. But the point, I guess, is that whether it's in the Congo, whether it's here, whether it's Eftali, we've both seen that lava. Ethiopia, wonderful. It's the same process. It's the same physical processes going on, and that's the thing is. Volcanologists go around the world looking at different volcanoes to look at fundamental process of how volcanoes work, how the planet works.
And that's the thing to remember, isn't it? I mean, it's very easy to think that we're on this slightly inert lump of rock floating about in the universe, but it is an incredibly dynamic planet we live on, and we hope to really be celebrating that over the next 3 nights. But sadly, we're almost at the end of our first show. Don't forget that you can still send in your questions on bbc.co.uk/Volcano Live. You can keep an eye on those volcano webcams on that, and the web chat with Dr. Clive Oppenheimer is continuing, and you can tweet us on #Volcano Live. Apparently we're trending at the moment.
What does that mean?
Get us, I don't know. What have we got coming up tomorrow?
Oh, well, we go to Chile for an incredible eruption that's still going on, and it's turning this forest ghostly white. Look at that.
That is incredible. I'm back in Iceland telling you the remarkable story of a community that took on a volcano.
And we're also going to move to a different part of the same volcano where we're going to see just how destructive lava is.
It is the most unbelievable landscape. It's just over there, so don't forget to join us at 8 o'clock tomorrow evening. Have a very good night. Goodbye. Aloha from Hawaii.